Polytopal realisations, non-crystallographic dissociation.
Okay, so first of all, I want to thank Emine and William for setting us here and giving organizing this nice meeting in a very nice way. Next,
Is it the top of that mountain we went?
yes. Yeah. Okay. Yes. Next, so before these days, before starting to speak about mathematics, I always need to give two statements saying that I am supporting Ukraine and I'm supporting people in Israel, and obviously I'm also supporting all peaceful people everywhere in the world. There are many struggling people at the moment I'm with them. And now I can really go to mathematical part. And so I'm going to speak about the project I initiated by Emine a couple of years ago, and a number of years ago. So together with Emine and the five we made some paper. Now it's published. Towards the end of the talk, it will be, so most of the talk will be about non-crystallographic realizations of associahedra. I'm going to tell about all these words, since it's not exactly what people are thinking there. But towards the end, there will be also some ongoing work, if I will have some time, this time when the matters come. So, what is an associahedra? Very roughly, it is a polytope similar to Christine, but maybe a higher dimension. So I don't know. Is there anyone who haven't seen a associahedra? They're like, so probably everyone has seen it from, yeah? Yeah, okay, but I will still show a couple of historical slides. So for me, one of the important realizations definitions will be through triangulations of n+3 bonds. So you draw the triangulations and you connect the ones which are different by a flip. And yeah. So you get some complex with whose spaces are partial triangulation. And this object turned out to be connected to many different things. And combine many familiar names in this table. And I'm not going to go through it. So this was the first historical appearance testing in Tamari states. So through a society with a law, and Tamari himself noticed that if you draw this nicely, it looks like a polytope. Now, not everything what looks like a polytope is a polytope. In 2 dimensions, yes. In 3 dimensions, there are some theories saying how to determine that in high dimensions it's much more difficult to find out whether you have a polytope or not if you have no explicit realization. And so there was a question: is there an explicit realization for this, especially in high dimensions? And so Tumarkin gave some realizations, but in his examples, not all some points were sitting in a convex hole of some other points, so it was not really like that. It was a convex thing, but not every points were needed. There was a similar realization from Jeff Stashev, but even curvilinear, coming from theoretic construction, and there was a big development several decades before Mark Hyman constructed an associahedron like real realization of three-dimensional associahedra, and he gave the name to the polytope. Also wrote this construction down, but never published because while he was preparing this, better realizations occurred, and so he's one letter. You can find his or his work now online, but it was never published. And since then, there were many other realizations. They were. It's possible to one can classify them like in several groups, and we will be speaking. Or we will be discussing the one after the company and the link and sending the plan. So now I'm so far what I was discussing was associahedra coming from associated law or from translations and in associahedra. Now I need to define generalized associahedra following Pavel and Yildirim, who introduced the notion of compatibility of rules in rule systems and used it to construct some combinatorial complexes of generalized associahedra for all. What this? What this? I didn't touch anything. Yeah, so generalized associahedra for all non-orientable systems, and the generalized associahedra were exactly the started associahedra from type A when we start from type A system, and then this was also used to this compatibility was used to obtain Polytopal realization of generalized associahedra for all these types. So now I'm going to recall the construction a little bit, so that we had the definition of generalized associahedra. If you know this, probably many of you do know, you can sleep. I will tell you when to wake up. So you start from root system. I will accompany with two-dimensional picture because I'm not able to draw a better one. So root system with all usual definitions of well-chambers round roads. So take one of them and take positive roots in there. I have marked the simple rules, but you want the positive one, let's say they make a call, and take also so take all positive rules plus negative simple ones. So we get the 5 results, and this since will correspond to the faces or high dimensional faces of generalized associahedra. Now, if I want to make a polytopal, I need the faces, but I also need to know who would intersect who. So it's just an example for A2 and the 3. So for which faces intersect and like in which combinations, and this will be sorted by compatibility condition given like the following. So let's start with one of the.
Is it possible to give the definition of associahedron, or is complicated? I don't know what the definition is.
Okay, so the definition of type A associahedron. It's you take triangulation, all possible triangulations of n+3 connect and connect that maybe it's yeah, we take all triangulations of n+3 and connect the two if they change just by one diagonal, like here. So for example, this and this, they have these diagonals, but this one is different. So you get a one skeleton of this polytopal, and the faces of this polytopal are partial triangulations. For example, on this face, everyone has this vertical. So this is type A associahedron. Now I'm in the process of giving the definition of generalized associahedra. So this is exactly what we are doing. How to do this for all root systems. So that for type A it will be this. Yeah?
But in any dimension.
Any
No, any dimension.
any dimension, yes. So far we take all almost positive roots, so positive plus negative simple. 5, 10. So this doesn't come so alpha 1, alpha 2, alpha 1 plus alpha 2, positive ones, and minus alpha 1, minus alpha 2. Negative simples. And now we want to find out which faces should intersect which one. It will take me a little bit of time to oh my God, a little bit to explain. So since all of these density diagrams are trees, we can color them black, white, like methylpeptide white. Yeah. Let's do this, and then denote. Let's have two separate subsets, black and white, and let's C black will be the product of all black reflections, and C white will be the product of all white reflections. I don't care in each other because all whites come with each other, so I just write them. And look at this prototype Foster element, product of black and white. Now I need to define two involutions. There will be a white involution and the black involution. What would the white involution do? If when I look at a negative black root, negative black will stay where it is under the white involution, and everything else will be to everything else. I will apply all the white reflections which I have. So it's easy to check it as an involution. This is how it looks for A2. So negative simple stays. So negative black stays under the white, and everyone else goes around. So I keep these involutions here because I'm going to use them. So what next? Next, Emine and Zelinsky showed that there is a unique binary relation called compatibility on the almost positive roots, so positive and negative simple, such that this compatibility relation is preserved by both of these involutions, black and white, and for negative simple roots, they are compatible with all roots which are expressed without using this element. So what does it mean? Let me take negative alpha 1, this one. When I what is it compatible with? It is compatible with everything it doesn't contain. So alpha 2 minus alpha 2 and Z2. This and this. And similar negative alpha 2 is compatible with alpha 1 and negative alpha 1. So I get this compatibility, this compatibility, this compatibility. And then I also apply this involution. I get two more. So this is what we would have. So this was just the compatibilities. And the statement is by Emine Zelinsky is that all maximal compatible sets are of the same cardinality n. And if I have some set and I removed one element, there is a unique way to replace by something else, which is exactly looking at the mutation rule in classical algebras. So flipping general rules in triangulations of polygons. So the generalized associahedra for any type in any dimension would be the following thing. So its vertices will be maximal compatible sets, and faces will be compatible subsets. So in this picture, it is just the rule to what I was drawing initially. So the maximum phase should be the vertices should correspond to maximal compatible sets. So this yellow thing is the associahedra.
So the compatible set means any two elements there are related. I mean, one is related to the other. What is compatible set? That any two elements in that set.
Yes.
Is,
Yeah, you're right. Yes. Okay, so with this definition, they got complex, and we're able to prove that each of these complexes produces some polytop in the space of the corresponding dimension. Now, let me slow down a little bit and return to type A. What does it all mean in type A? In type A, you just so let's start from, let's take a triangulated n plus trigon with this sort of zigzag triangulation. And let me label the diagonals in this triangulation with negative simple rules. Minus alpha 1 to minus alpha n. Now, for any other diagonal, if I scroll, I will label it with all the diagonals I'm crossing on the way. So this one crosses minus alpha 2, minus alpha 3, minus alpha 4. So the diagonal will be labeled by alpha 4 plus alpha 3 plus alpha 4. What is a compatible set? I'm claiming that compatible rules correspond to non-crossing diagonals. Why? I need to check two conditions. One should be invariance or under those two involutions, and the second one is for negative simple rules. So to be compatible with negative simple rules means that you need to not contain this simple root in your expression. To be not intersecting some particular simple negative simple root means exactly that you don't read this in your expression. So the second condition is exactly from the definition. While the first condition resolve everything by evolutions. So what are these evolutions doing here? It's actually easy to check that one of them does make a reflection with respect to the vertical line orthogonal for all this. And the second is the reflection with respect to this line. Which means that reflection doesn't change the property of not intersecting. So the evolutions preserve this property, and indeed, we see that compatible rules are non-crossing means non-crossing diagonals. So we get a generalized associahedron in type A. Is expressed by non-crossing diagonals, which is exactly the definition we used for Tumarkin. Yes.
These compatible sets, do they have anything to do with parabolic algebras?
No, I was not think so. Okay. So.
I'm sorry, I think I forgot, but what was the, let's say, condition for the Tumarkin Polytopal?
And there was one definition through associativity, but we also had this definition through associativity is a Catalan property. Yeah, well, it's a Catalan object. You could replace this by more or less any other Catalan object and draw the same picture with and in particular with triangulations, like the picture with triangulation. So what we see here, this definition for type A exactly gives so compatible sets are maximal compatible sets are maximal sets of non-crossing diagonals, which means triangulations. Okay. Okay. So it's That's what I tried to explain. So with the faces labeled by the corresponding roots, and you can see that, for example, so my negative symbol, its neighbors are exactly everyone who does not contain algebra. Yeah, so it all fits. This is the pictures from paper by Pavel and Zelensky, like realizing this in coordinates with polytopes. Okay, type B. And so we got the definition of generalized associahedra from Emine and Zelensky, from Emine and Zelensky we got the Polytopal realizations. Then Marsh, and Zelensky extended the combinatorial construction of the definition of generalized associahedra to all cluster elements. So you don't need these assumptions anymore that those exactly this cluster element and always along internals produce realizations for them, and then there will require many generalizations of different constructions. One would say that question is closed here, but also Emine and Reading observed that you can do the whole construction without assuming crystallographic conditions. So you don't need this to be an integer number actually to do all this stuff. You can do all those definitions without them. And so what do you get? In addition, then you get the hedral group of symmetries of a polygon plus H3 and H4, so the group of symmetries of icosahedron and the four-dimensional analog of that. Yeah. So can you also obtain associahedra for them and realize them in polytopes? I mean, for the hedral group, it's very straightforward. It's two-dimensional. It's a polygon. Polygon is always a polygon. Yeah. So for H3, it's just one picture which is easy to redraw in a different. So this is a picture from Pavel Reading. It's easy to redraw this in a very convincing way. So and see it is a polygon. For H2, for H4, it would be probably harder. I didn't try to do it directly, but what we are going to do, it will be like a uniform construction to obtain all of them once from the same construction. Yeah. So I think by now I said what are non-crystallographic associahedra. And here is the problem is that the usual tools to work with associahedra were not there to play with them. And so in the next part of the talk, I will tell you what we did. But before that, so I have a little commercial break. So here's Pavel, my colleague in Durham. He is a number theorist, but in his free time, he is used to 3D print some nice mathematical objects, and he does some jewelry, like from metal, really nice things. He has an online shop which is not really working yet, but it will come soon. So he also has an Instagram page. He said currently when he has problems with online shop, it's better to just write to him if you like something, because in particular he has really nice small associahedras like all the size metallics are very nice. And you are very welcome to drop me. I mean, it's easy to find his email, and he will be happy to show what he has. Okay. So now back to realizations. I mean, this is really realization.
Not commercial realization.
Yeah. Okay. So I will. What we use is originated from the work of physicists then having by 18 kinematic associahedrons, this is a picture from their paper. And they constructed something to study scattering particles. I don't know anything about that, so maybe you know. What they did, they obtained a space of realizations with many parameters for type A, and then Q with his team, including Emine and Thomas here, obtained a realization for all Wimpy types, so all simplified types, ADE. Now I will need to tell what they did. It will be a little bit embarrassing for me because I'm not really understanding and they're sitting here, but I will try. So you have to correct when I'm doing something stupid. Yeah, okay. So since there are experts in the room, for experts, I guess the explanation would be you take an orientation of simply Lagrangian diagram, you take category of representations of the square, and then derive category, and then some collection of all indecomposable objects, yes, that is shifted projectives, and then you take a large vector space of the dimension of how many objects you have seen there. For each of them, you will have one variable, one indeterminate, and for every mesh, you will have a parameter. And then for every mesh, you will write an equation like this. So I guess the experts probably didn't understood what happened. I am not an expert here. I need another explanation. So an explanation for me would be, okay, this line I still can read. It is a Dinkin diagram. I put some errors. I get a quiver, which is an orientation of a Dinkin diagram. Then I draw this so that all errors look sort of to the right. I make many copies of them and then connect them this way. So I'm fine so far, yeah. Okay, because at this point it starts to be too abstract for me, so I will make a little picture so that I would still know what happens in type A. In type A, I had the angulation, the square corresponded to this, so I change the direction of the arrow each time the direction of the front change, so the this direction. Yeah, so I get this, and now I draw them in a grid. These diagonals, one diagonal at every spot. The thread diagonals from the triangulations are forming in this zigzag. I'm doing this. And what happens with the diagonal that I move? That way, I move just one end clockwise. And when I go downwards, I move the other end clockwise. And then I organize all my diagonals this way. So let me redraw the same like a little bit in a bigger picture. Infinitely long strip of the diagonals, and you see it starts to repeat. Obviously, I don't know need that much of that, so I will take the fundamental domain of that. So there is a shift like this, but there is also, yeah, will be the same as that, but yeah, bottom to top. So I take the fundamental domain, and this will be the part where my variables will sit. So with this, I'm ready to return to the table. So far I put this. Now I need to make a space where variables correspond to each of these dots in this region, and parameters will correspond to the squares, the diamonds, and equations will also correspond to the diamonds in the following way. Every time I see the diamond, I will put a parameter inside and equation saying that this plus this is equal to sum all of them. What does it mean in an example? So let me take a very small example like this, E3. And here are all the possible diagonals, and in particular the 3 diagonals are here. And there are 9 diagonals. It's interval, I have 9-dimensional space. So 9 variables in red and 6 parameters in blue, sitting in all the squares, including the boundary ones. I get 6 equations for all of the writing the equation for all of the meshes. And if I will make some choice of parameters, I will get some realization. For example, if I put all parameters to be 1, I get this nice picture and made by Emine. And so this is what, yeah, does it make sense for everyone? Yeah. Now, the plan is to use this to construct realizations of non-crystallographic associahedra. That was the original idea of Emine. She said, we have this, probably we can use something to get everything through folding techniques. So let me now speak a little bit about folding or unfolding. So the idea is whenever you have a non-simply laced root system, there is a simple laced root system sitting under it. For example, for H4, there will be a E8, and the idea will be that the groups of roots from the big simple laced one will project to some roots of small but not simple laced one. And this idea is often can be used to generalize statements from simple laced to non-simple laced. So let me show a little bit more. First of all, if your non-simple laced thing is crystallographic, what happens is actually just a projection. Like you can A3, you can project it to P2 orthogonally. Just table of all these cases. It has some weights which are trivial in this case because it is crystallographic and just a projection. In non-crystallographic case, this weights will be a little bit more non-trivial. In this case, you will project to not directly to non-simple laced root system, but you will project to the original non-simple laced root system plus scaled one. And this coefficients of scaling, they will compute for H3 and H4 by moving Pavel back in 93, and more recently for the dihedral group by Durham and Pavel. So just to show you complete table of all these projections. In case of H3 and H4, the comment is these weights are Gaussian ratios, and all other cases there are some Chebyshев polynomials. Okay, so and just one more I think to give you an idea how everything works. So we take E8, we want to project this through H4. On the level of the group elements, let me label them like S1 to S4, Q1 to Q4 in this way, and call this Ri, so that Ri are these products. Then it turns out that these Ri's produce exactly the same relations as the one we see in H4. Which to me this looks really like a miracle, because you started from something which looks simple laced, and then you somehow get fifth degree here from where. And this also works on the level of the root, like in algebra also works nicely with this coefficients. So now let me try to use this to obtain associahedra for all non-simplicial types, non-crystallographic ones including. So I'm going to get all non-simplicial. So this is the theorem together with Pavel and Emine. Let's take a finite root system, finite not simplified root system, and let's say it's unfolding, simplified unfolding. So something which projects to something simplified which projects nicely to our non-simplified root system here. We know associahedra for this ones, and we want to get associahedra for this one. Smaller but more complicated. Now let's take an associahedron for the simplest one, but we had a big variety. We had many parameters. Let's choose the one which is sort of symmetric, is the correct symmetry. So in the crystallographic case, we will just take the ones where the corresponding parameters are equal. In non-crystallographic, we will take them with exactly the same weights, like this Gaussian ratios or Chebyshev polynomials, which we have seen in the table. So take this symmetric realization of the simplified associahedron, and now consider a plane which is obtained by intersection of all planes like this. So I put the condition again in crystallographic case. I just impose the condition that two variables are the same. In non-crystallographic, they're coming with the weights. And I take many conditions like this. So for all places where I project two variables to one, I take a condition. So I take the biggest associahedron and intersect with a plane of some dimension, smaller dimension. It's not a hyperplane, so it's some space of some smaller dimension. What I get exactly the associahedron for this non-crystalline. And this is the statement of the series. Let me try to illustrate this. You remember this picture. This picture was obtained for AC with all equal weights, weight 1, which is very suitable for us here because if I want to project AC to B2, B2 is B2 is crystallographic, so my base will be one. So all of this realization fits well. Now I also I also need to impose two conditions that this coefficient equal to this coefficient is equal to this. So yeah, it is false here. And in addition, I intersect this with the plane given by so this equal to this, it is equal to this variable is equal to this. It looks like many different conditions, but in reality, in this case, it just gives me this plane.
Do you have to worry when you do that as some vertices because you're not extreme?
Not really, because yeah, I mean, you just look at the funds and you see what happens. So, what do you see here in this intersection is a hexagon, which is exactly an associahedron for time B2. Yeah, so this sort of fits. So does that make sense? So I take big realization for that, then I apply all symmetric conditions cross with the plane of some smaller dimension and get exactly the associahedral form.
So if I understand correctly, folding idea of Tumarkin is actually in the associahedra, it's actually more like an intersection with this pi.
Intersection, or you can say it is actually a sort of orthogonal projection to that.
Yeah,
So the proof is that everything orthogonally projects, all the funds orthogonally project, the G vectors orthogonally project, so everything orthogonally projects. And this is, it's not hard to prove this, but this is what we need for that.
So if this they keep finding then get it as a sublet. Thank you.
I didn't quite get what you asked.
So does it present the joining element?
Okay. Does it present?
Generalized associahedra has projects.
Again, there is a little bit of joining bit of work. So you see the spaces here. There's sometimes intersections with. There's sometimes the edge, sometimes intersection with the face. So yeah.
And if I understand correctly, I would say it's also point fishes. No, so it's not really gonna be lawyer stuff like that. That's okay.
Yeah. Okay, so this I wouldn't say that, don't stop here. Now, just a little remark about some sources. Crystallographic phase can be also derived from the local physicists. That's why they call it non-crystallographic ones. I guess never I've heard anybody else. And the space of all polytopal realizations of G vector funds in crystallographic case is also called really nicely in Pavel Polytopal. And there are a couple of nice surveys on the associahedra if you want to see more. Now I want to switch a little bit. So maybe any questions here, because now I want to switch to some ongoing work in a little bit different situation. So any cases, any questions here? So the idea is that the same idea of taking something and crossing with the plane of symmetry can be used in some other situations too. And namely, we are going to look at the associahedron for the stream. And now, like very recently, about months ago, we got that there's also Polytopal. And this is an ongoing work with Pavel and Salvatore Stella. So let me say what's going on. In 2011, Pipon and Polezi and define quasi-cluster algebras from non-orientable surfaces. So you take a non-orientable surface, which you can understand as like a usual surface, but sometimes you see a cross-cup on it. Cross-cup means you cut out a disk and identify the object points of that, and get a non-orientable surface, and then you can triangulate it and have all the same business as we normally have on triangulated surfaces. So you can build an associahedron from that. You can like a complex. You can also think that this is a hyperbolic surface with hyperbolic metric and measure the distances and get cluster variables. Quasi-cluster variables. Why cluster? Because the exchange relations are not always having two terms, sometimes they have three terms. And the main difference is that sometimes you also see a closed curve coming through the cross-cup. So it is a one-sided closed curve. If you take a little neighborhood of it, you will see maybe strip. And then one can ask when such a thing results in some finite complex, so when this gives some sort of quasi-cluster algebra of finite type. And it turns out it's only finite type when the surface is a Möbius strip with as many points on the boundary as you want, but as soon as you add some more topology to it, you immediately get something infinite. So let's take a Möbius strip. Let's build this complexes from that. So this is Möbius with one more mark, with two, with three. And one can ask whether you get from these complexes, whether you get a polytopal or not. For example, I don't know, looking at this picture, it looks like a polytopal, so it's a natural question to ask. And John Wilson, so my former student, proved that it is some shellable and spherical complex. He didn't go to really prove it as a polytopal one, but he was able to prove that it is a spherical. But the paper itself was like the construction was sort of very technical, long, and in some sense not satisfying, and not even also not technical to the point that it is a polytopal. And now we want to get this associahedra from our construction. So the idea is that we can lift all these quasi-triangulations from Möbius strip to the annulus, and to get, and then when you lift it, it is a two-fold cover, so there is some symmetries you can try to identify and use the symmetry to define this crossing. Now the first problem here is what you would cut, because there is no realization of a associahedron for the annulus for fine case. So what we do, let's take the G vector form for A and N. So I can only draw A11, not, and so this is G vector form, and we will add all cells of the dimension 1 containing imaginary root. So this line corresponds to the imaginary root. It will eventually correspond to this one-sided closed curve. And what we will do, we will cut this picture by some plane, and all these infinite events will stay out of this plane, and in this intersection we will see some final picture which will be exactly having the combinatorics of the polytopal we need for our Möbius strip. Now a little problem here. I mean, what we expected initially was that you draw symmetric scenes, then you draw the G vectors for them, and the symmetric scenes should probably project to the same thing. But no, since they have, you can see from this picture that symmetric scenes, so symmetric from 2 to 1, from 2 prime to 1, they do have a little bit different G vectors. So between 2 and 3, and here it starts between 1 and 2. And that's why actually we need to shift them a little bit. So the real symmetry will be you take something and you take a curve here, and the copy of that will be shifted one step to the right. Then they will have almost the same but with negative G vectors, and you will be able to play the same game with intersecting with some conditions and getting the associahedron on the for this Möbius case. And finally, I want to thank you, but maybe since I have 1 minute, I want to say one more word, namely, from what I'm saying, it feels like you always get the polytopes and it's all trivial. We do have some procedure which realizes, which produces associahedra in all possible types, but for types H3 and 4, we can produce without. So in crystallographic cases, we will reproduce with this procedure the same associahedra which you normally get, but in type H3, we can get some complexes living on the terms. And this is coming from realization, geometric realization by partial reflections when you reflect some of the vectors and keep some of the others. So it's not totally trivial. So thank you.
Thank you. Any questions, comments?
When you apply the unfolding different weight than WI to 1, do you also have a triangulation picture for that one as well?
Unfortunately.
What does it mean with the partial reflection?
It
shows that.
So you can you can start from some vectors. Maybe I will first yeah. So A3 case. I'm drawing the projection of A3 to like stereographic projection. Let me take this domain and I want to put a little quiver inside that, like this. A3, yeah. Now I want to apply the mutation to this domain together with this quiver. What I will do, I will keep the side. Let me reflect with respect to this side. So, yeah. When I reflect this side, I will keep the space, but we'll say that the vector corresponding to that is now we change the sign. For the end of the tail, so this phase, I will reflect it with respect to this. So I get this one. And for this side, it is the head of this vector coming to the side where I want to mutate. I will just extend. Partial means that I reflect the tails and extend the heads. I get the new domain. And then if I also get some quiver shades will be like this. And then I continue to do this and I get a tiling of my plane by these curvilinear triangles containing more than one, sometimes containing more than one phase, more than one triangle of the initial. And then the tool to that is the associahedra. I can do this in all the types, and if I will start in H3, but so not from the triangle with angles 5 over 2, 5 over 3, 5 over 5, which is a 5 over 5, which is the fundamental triangle normally, but with the double of it, like this. If I will start this procedure with that, I will get this guy, and there is also another possibility to get this guy.
Question. So if not, let's thank Anna again. We meet at 11:30.